All right, recording is rolling. Welcome to Tuesday, May 9. So again, doing a little bit different things with different classes because classes are a little bit off track. We're in this testing season. So right now we're continuing the final exam review. I've got this recording. I will post this eventually to Google Classroom. Now, you guys remember how this is working is the final exam is going to be closed notes. But open calculator. So if you use a calculator, I've got a class set of these. This should be like plenty of calculation power. You guys have in front of you this study guide with every single question that's going to be asked. Right? The only difference between what you guys see in this review and what you'll see on the final exam is that some of the numbers might be changed. So like here, I've got 8 newtons and 5 newtons. Maybe it'll say like 10 newtons and 3 newtons, right? So, okay, right. It will say like 9 volts instead of 5 volts, right? And also these answer choices are just going to be scrambled in a different order, right? But besides that, it's going to be the same questions. Okay, you guys got that? Okay. So even though it's closed notes, you guys should probably be taking notes during this review. You guys study those notes. There are a few like simple equations, maybe like Ohm's law, that sort of thing, right? And then these questions are like predominantly conceptual. Right? And I think if you've been paying attention this semester, and you know the stuff and you study this and you're paying attention during this review, then you're gonna be all right. Okay. Right, you guys good? Right. Want to mention too, yearbooks available in senior dining Monday through Thursday this week. If you haven't pre-ordered one yet, then they're accepting $105 cash only for one, right? But only while they last. All right, so you guys good? All right, here we go. Let's pick up where we left off. All right. So when a river narrows, the water in the river flows. So we're looking at these materials type questions. This is a conservation of flow question. Okay. I think we may have covered this. I don't know. Right, let's see. Right, so we got a river, and the river's going to narrow. Right, you guys see that? The river is flowing like left to right, and it narrows. Okay. Now I'm going to change the river to a pipe system because that's how I did it in class. It's like the same idea. Right. So this is called conservation of flow. Right. We have some area 1 here, some area 2 here. Right, guys, yeah. Right. And I've got some speed 1 here and some speed 2 here. Right, is that true? Right. Now, if it's the same like gallons per minute everywhere, you say same cubic meters per second, what that ends up being is the cross-sectional area times the speed ends up being the same in both parts, as long as the liquid is not compressible, which is basically true for water. So we're doing that. Okay. Right. So when you have a smaller area, what has to happen to the speed? Has to go faster. Okay. Throwing a numerical example. Right. Suppose this was like 6 units and 4 units, maybe meters squared and meters per second. Okay. Okay. And then the area gets cut in half. The cross-sectional area. Let's say this area is half of that area. What's the new speed?
Twice.
Yeah, twice as much. 8 meters per second. If I attach units to these, right? It's like square meters, meters per second, meters per second. Because 24 units equals 24 units. Okay, you guys got that? Okay. All right. Is that everybody good there? Here. Oh, if you blow across the top of a piece of paper, the paper will. Ooh, well, we can try that out right here. Here. And on the exam, if you forget it, you can try it out too. So I got this paper, we blow across the top. What does it do? It lifts. You guys see it lifts? Okay. Is that called Bernoulli's principle? Bernoulli's principle? A fast-moving fluid, the internal pressure decreases. That's Bernoulli, isn't it? Okay. Which can also be related to this conservation flow. If there's a fish swimming around the pipe system, the fact this water picks up speed, does that also decrease the pressure? That's Bernoulli's principle. Right? Temperature. Oh, okay. I think we're moving on to thermodynamics, which thermodynamics and heat transfer, which is like the first topics we actually talked about this semester back in January. Temperature is mostly related to the. Hey, do you guys remember just a week or so back, we were talking about Maxwell's demon, and it had to do with this idea of like if you have these 2 chambers side by side, get these drawn. Right. And if you could somehow let all the hot molecules, fast-moving molecules into one side and all the slow-moving molecules to the other side, that this side would become hot and this would become cold, right? And that's kinetic energy theory of temperature. Like, why does something have the temperature that it does? Well, it has to do with how fast are the atoms vibrating, right? You guys remember that? So let's go back here then. Temperature is mostly related to the, what are you looking for? The total energy of something? No. Total kinetic energy? No. Average molecular kinetic energy. Hey, I like that one. Right. Average energy? No. Average kinetic energy of an object? No. Okay. Average molecular kinetic energy. Okay. That's what's going to make something temperature. Okay. Right. You guys good? The reason an ocean's temperature doesn't vary much from season to season, right? Guys, isn't it really difficult to heat up and cool down water? Let's say you have a pot of water, right? Throw water in a pot and you throw it on the stove. And you turn on the stove and you wait about a minute. Okay, 1 minute, the pot's been on the stove. Do you want to touch the metal of the pot? No, it's gonna be hot because that metal heats up real easy. Okay. That water though, has that water heated up very much after 1 minute? Not after 1 minute, right? So the heat transfer, that's your delta Q, heat transfer equals mass times specific heat capacity times the change in temperature. This is change in temperature. M is mass, right? And C is specific heat capacity. Right? Would that be true? Right. So if you put some amount of heat energy into something, right, and if the temperature did not go up very much, that's because there's a huge heat capacity. Water has a huge heat capacity. Water, you can dump lots and lots and lots of energy. And because this heat capacity is so large, the temperature barely changes at all. Right? Or if you like, here, I can sort of rearrange this. Let's go like delta T. How much does the temperature change? Well, how much heat energy did you put in, divided by how massive is it and specific heat capacity, right? You can take this top version and sort of rearrange it. It might look like that, right? So, large heat capacity results in a low temperature change, right? So it's hard to heat up water. It's also hard to cool down water. Now let's go back to the ocean. The ocean is lots of water. Right? Doesn't change very much from season to season. Let's see, there's lots of fish in the ocean. No. Ocean located next to large landmass. No. Large land areas now. Water has a high specific heat capacity. That's this whole explanation I've just been giving you. Right? Oceans located in mild reaches of Earth. No. Water has a low specific heat capacity. That's the opposite of the answer. Right? Okay. So water has a high heat capacity. It's difficult to change the temperature of water. Okay. Okay. Thanks. Here. Okay. I'll get it. The largest extremes in temperature are usually experienced. Okay, largest extremes in temperature. Let's take a look at the choices. Near large coastal cities like San Francisco, which is surrounded by water, near the oceans, which is water, in the middle of the continent, not very much water, in Japan, which is surrounded by water, on islands, which are surrounded by water. Guys, which of those options stands out as different from the others? Middle of the continent, right? Middle of the continent, right? That's low heat capacity. How many of you guys have ever lived out in the Midwest on the plains? Anybody? Right? Yeah, crazy temperature changes. Really hot days, really cold nights, really hot summers, really cold winters. Right? Like Florida's more like mild, right? We don't have crazy temperature swings usually. Right? It's really great, right? Okay. All right, you guys good there? The fact that desert sand is very hot in the day and very cold at night is evidence that sand has a what? Low heat capacity, right? That's the opposite of water, right? It's really easy to change the temperature of the sand. Right? When an iron ring is heated, the hole becomes, ooh, this was a Paul Hewitt demo. I remember took a whole day just to watch a bunch of Paul Hewitt demos that related to thermodynamics, materials, that sort of thing. Okay, let's not do the ring first. Let's do like a bar. What if you have an iron bar? Guys, if you heat up the iron bar, does it expand? Yeah, it's going to expand. Right? Now let's go to a ring. Right? And okay, of course, the ring has a hole in the middle. That's what makes it a ring. Right? So here's all your metal right here. This is metal, metal, metal. Right? Okay. And we're going to heat this up. Right? Now, guys, does the metal itself expand? Yeah, the metal itself expands. What about the hole in the middle? Does the hole also expand?
Yeah.
Yes, it does. The whole thing, as long as you heat it uniformly, the whole thing's going to expand uniformly, hole and all. Now, the Paul Hewitt version of this was, I think he had like a ball on a stick that he could like barely push through when it was at room temperature. It was a tight squeeze. And then he went and he heated up just the ring. And then the ball, you very easily, the ball on the stick, very easily went through the hole. Right, you guys remember that? All right. During a very cold winter, water pipes sometimes burst. The reason for this is, right, now most materials you heat them, they expand. Water is a weird kind of exception. Guys, does ice sink or float? It floats, right? You put an ice cube in water, it floats, which is evidence that ice, the density of ice is what compared to water, less. So you freeze water and it expands, right? It goes to like a crystal pattern. It's what snowflakes have 6 eyes, I'll do. Okay. So does water expand when it freezes? Yes, it does. And so if you got water in a pipe and it freezes over, got to be careful. Okay? Remember, calling my brother the other day, who lives in Pennsylvania. He was talking, well, I guess a few months back, he was talking about this being the case. He said, "Oh yeah, we have water in our pipes, and we're supposed to drain the water before this crazy freeze storm comes over." A bimetallic strip will bend when heated because. Ooh, let's look at a bimetallic strip. Okay. This was another Paul Hewitt demo. Okay, let's come up with these questions. Okay. So we're going to have 2 different kinds of metals here. Okay. Oh, yeah, pick any 2 metals, maybe like iron and copper. I don't know, it's just 2 different metals. Okay. 2 different metals. Okay. And we're going to heat this thing up. Okay. Now, do you think that these metals expand at different rates? Because they're different materials, they probably do. Right? It would be kind of a crazy coincidence if they expanded the same. Right? Side note here, you might remember actually steel and concrete expanded at about the same rate, which allows for steel reinforced concrete to exist, right? Luck of the universe, right? But most materials are just going to do their own thing. So if, let's say, the bottom material expands more than the top material, is it going to bend kind of like this, like a smiley face, you guys think? Right? Because bottom one's expanding more than the top. Okay. Let's see what answer choice says that. Bimetallic strip will bend when heated because each metal expands at a different rate. Oh, that's exactly what I just said. Right? Each metal expands at a different rate. Okay. Okay. You guys can figure that out. Heat transfer by conduction in metals occurs when? Do you guys remember the 3 main kinds of heat transfer? Heat transfer. Let me write them down. We had conduction. What were the other 2? Convection and radiation. Good call. All right. So conduction, is that direct contact to surfaces? Right.
Yeah.
Convection, could that be like a steam cloud, or how about like the Gulf Stream is carrying warm water from the equator up to the poles, right? This convection current. Now radiation, is that like how sunlight gets to Earth through the vacuum of space, right? In fact, radiation is the only one that doesn't need a medium. It can actually travel through the vacuum of space, right? These first 2 can't. This one can. All right. So let's go back to the question then. Heat conduction in metals, heat transferred by conduction in metals occurs when, say, atoms give off heat in the form of EM waves. That sounds like radiation. Large numbers of atoms move place to place. That sounds like convection. Electromagnetic waves are right there. We're already off to radiation, so not gonna happen. Electrons bump into atoms and other electrons. That sounds like conduction to me. You guys think that one sounds like conduction? Electrons bump into electrons? That's direct contact to surfaces. Heat transfer by convection. Hey, convection occurs. See, electromagnetic waves. There's radiation. Atoms give off heat in the form of EM waves. Radiation again. Electrons bump into other electrons. Well, we just said that was conduction. Large numbers of atoms move from place to place. There you go. That could be the Gulf Stream. That could be a steam cloud. That's convection right there. Heat travels from the sun to Earth by what process? Radiation. Boom. Electromagnetic waves, that's radiation. Okay. Now, radiation doesn't necessarily mean ionizing radiation, which is going to maybe immediately give you like cancer or something. But although, you wouldn't want to stand UV light too long, but yeah, like just visible light or infrared light. Yeah, it's like radiation. Which cools at a faster rate? A pot of boiling water at room temperature or a pot of lukewarm water, also at room temperature. Same mass, same. Okay. All right. So I want to draw this one out for you guys. Right. This is something that Isaac Newton was interested in, and he came up with something called Newton's law of cooling. I think this was one of the posters that came up with you guys too. Suppose you have a pot of water. Right. I see my pot of water right here. Right. A little handle on that. How about that? Okay. And it's all sloshing around there. Just trying to draw it all even. Okay. I got a pot of water, and it's really hot water, so it's emanating heat. You guys see it's like emanating heat, all this like heat leaving. Right. And I'm going to throw a thermometer in here. Thermometer. Okay. And I'm watching it cool down as the day goes on. Okay. You guys see that? Okay. So let me make a graph because I made some axes here. I'm looking at the temperature, maybe I don't know, degrees Celsius, for example. It could be Kelvin, whatever. As a function of time, you know, whatever time you, I don't know, seconds, hours, whatever. So I'm watching. Now it started off really hot, so I'll call that T naught. Right? Some initial temperature at time 0. Right? Now, do you think if I leave it alone for like 5 hours, it's going to eventually reach room temperature or something pretty close to that? So I'll call that T environmental, like environmental temperature. Right? And I'll make that a horizontal asymptote. This is my horizontal asymptote. Okay. And I'm watching the temperature as a function of time, and it's doing something like this. Right? So do something like that. Okay. And there's an equation that goes with this. It's called Newton's law of cooling. Okay. Now the question here said, which change the rate of change? Rate of change. Guys, is that like the slope of this line? Rate of change is like the slope of this line, right? So let's look at rates of change. Yeah. So near the beginning, when it was really hot, here was the rate change was the slope of that line. After a few hours, when it's closer to room temperature, closer to the environmental temperature, the rate change is the slope of that shallower line, right? Isn't that true? Right, you guys got that? So, are we good? So what we got here? Okay. So guys, which line is steeper, when it was hot or when it's relatively cooler? When it's hot, right? If you like, sometimes students like me to say, right, if you're like climbing a hill, okay, see that's pretty level ground there. Ooh, now it's getting steeper. Ooh, now it's getting steeper. Ooh, now it's really hard to climb the mountain because the mountain's really steep up here, right? That's like a steep slope. Right, so greater rate change. So where was it? The boiling water is going to cool off at a faster rate. Okay. Right. You guys got that? Planet Earth loses heat primarily by what process? Give you guys a hint. Earth is surrounded by the vacuum of space. So what's the main way to dump off heat? Radiation. Radiation. Okay. Now there's a little bit of the top of the atmosphere being picked off by solar wind, but that aside, yeah, radiation is the main way. Radiation in, radiation out. At high altitudes, let's say you go up to Denver, the boiling point of water. Ooh, like here at sea level, the boiling point of water is 100 degrees Celsius, but that's pressure dependent. Up in the mountains, is there high pressure or low pressure? Low pressure, which means the boiling point does what? Also gets lower, right? It might be like 95 degrees Celsius, for example. Hey, do you guys remember reduced pressure boiling? If you take a cup of water and you put it in a vacuum chamber, what does the water do? Boil. Like even at room temperature, the water will boil, right? The boiling pressure, sorry, the boiling point, the temperature boiling point is lower in low pressure. When snow forms, the surrounding air becomes warmer. Because why? Now guys, when snow forms, is that maybe like water in a vapor phase or liquid phase turning into a solid, like crystal solid snow, right? So the snow itself is that undergoing a warming or a cooling process? That's a cooling process for the snow itself, right? As it goes from like vapor or liquid form into a freezing form, right? But guys, does that thermal energy just disappear from the universe? No. So So is it transferred to the surrounding air? And that pretty well walks through the scenario, doesn't it? So let's see what answer choice says that. Say changing from a vapor to a solid is a process that gives off energy. Oh, that sounds exactly what I just said, right? If you go from a vapor or a liquid to a solid, right? It's going to give off energy. That energy doesn't disappear, so it goes to the surrounding environment to warm up the surrounding environment. Right? Right. Laws of thermodynamics. Right. There were, well, maybe like 4 laws of thermodynamics. We really focused on the first law and the second law. Okay. So there's a question for each of those here. Right. The first law of thermodynamics is a restatement of what? Conservation of energy. Conservation of energy. Right? Energy is conserved. You can't create or destroy energy. You can transfer energy, take different forms. It's conserved. The greater the difference in temperature between an input reservoir and an output reservoir for a heat engine, all right, check this out. Yeah, the greater the efficiency. Good call. Greater the efficiency. Right. Hey, do you guys remember the Stirling engine? Right. Now, I don't have the materials for it right in front of me now, but right now, obviously, it's not moving. And why would it? It's just same temperature everywhere. But what if you take a cup of hot water and you put it underneath it? Doesn't that expand the gas underneath it? So it's right, expands and then contracts, and then it goes through the cycle and starts spinning. Isn't that? So it needs a temperature difference to make this work. So if you put a cup of hot water here, right? I think I did this in class, and then there was a Bill Nye video, did the same similar thing. Right? And then the atmosphere, like the room temperature, would be like the colder of the two temperatures, wouldn't it? You need a temperature differential, right? Right. So here's the equation that goes with this. The efficiency is equal to 1 minus the cold sink over the hot sink. Oops. Right. Sorry. Right. The efficiency is equal to 1 minus temperature cold over temperature hot. That's what I meant to do. Temperature hot. Okay. All right. All right. So I'll label this efficiency. That's Greek letter eta. Looks like an N with an elongated tail. Guess that. Right. Well, let's look at the equation form of what I just told you. Right? I mean, again, you guys keep whatever notes you like. This equation is going to pop up later here in a bit. Like right now, the temperature on the bottom, the temperature on the top are the same. Right? Let's call it, I don't know, 300 Kelvin. It's probably not too far from that. Guys, what is 300 Kelvin divided by 300 Kelvin? 1. What is 1 minus 1? 0. Hey, 0 efficiency, which means this thing isn't going to spin at all. Right? What if you had a greater difference between these two? What if this top guy's like 100 Kelvin? This bottom guy's like 500 Kelvin. Right, now we're kicking. Right? Right, guys, yeah. Okay. So the greater the difference in temperature, the greater the efficiency. 43. 2 identical blocks of iron, one at 10 degrees Celsius and one at 20 degrees Celsius, are put in contact. Suppose the cooler block cools to 5 degrees Celsius and the warmer one warms to 25 degrees Celsius. This would be a violation of what? Well, let's check this out. So 2 blocks of iron, right, put these guys in contact. Right, just like that. Right. And suppose this one's at 20, or what is it? I'm so sorry. Okay. Well,
One's 20 anyway.
yeah. Well, okay, well, one's 20 anyway. You're right. So 20 degrees versus 10 degrees. Okay. So those are the starting temperatures. One's at 10 degrees, one's at 20 degrees. Okay. Now, hang tight for a moment. Okay. What if we just started with that? Okay. And say this is an isolated, maybe like insulated system, and we walk away and come back like 5 hours later. Would you expect it to be pretty close to 15 and 15 degrees Celsius? I mean, same mass, same material. Yeah, I would expect it to reach an equilibrium of 15 degrees Celsius. Okay. And there is a law of thermodynamics that says that that process is going to happen in that order. And which law of thermodynamics is that? The second law, right? And then you could calculate the entropy change for each one, and the entropy overall would increase. Okay. So, okay. Now, what you would not expect to happen spontaneously is for this guy to pick up 5 degrees and this one to cool down 5 degrees, right? Now it can go from these more extreme to the less extreme spontaneously, but it's not going to go from the less extreme to the more extreme spontaneously. Okay? You could force that to happen. That's what refrigeration is, but that's an energy intensive process. Again, it's not spontaneous, right? Okay. So going from this top state to this bottom state would be a violation specifically of the second law of thermo. Okay? Would this also be a violation of the first law? No, because again, like same mass, same material. If one picks up 5 degrees and the other loses 5 degrees, in terms of conservation of energy, there's actually nothing wrong with that. But in terms of the second law of thermodynamics, the order of processes, right, that's all out of whack. Okay, you guys got that? Everybody good? Running a refrigerator with its door open makes the room all right. One of my favorite thermodynamics questions, guys. If we left this room pretty well sealed, and I left a refrigerator door open, is there a bunch of cold dumping out the front of that fridge? Yeah, there's a bunch of cold dumping out the fridge, but don't forget the what dumping out the back, all the heat, right? So it's kind of like, again, forcing this to turn into this, which is what refrigeration is. Here's your refrigerator door open. Ooh, got a bunch of cold dumping out one way. Don't forget all the heat dumping out the back. But there's one more thing, which is the fact that it's not spontaneous. You have to have the fridge plugged in. So you're importing energy off the grid to make this whole thing happen. What's going to win? The heat from the hot or the cold from the cold? The heat from the hot. I mean, that's a very colloquial way of saying that. But if you mix it all back together, overall, the room becomes what? Warmer, right? You're going to heat up the room. You're heating up the room, right? You guys got that? Okay, everybody good? We're good. 45, the ideal efficiency for a heat engine operating between these two temperatures is, notice they gave them to you in Kelvin, which is nice because you don't have to convert to Kelvin first, which you would have to do anyway, because, well, we're about to apply this right here, right? You guys ready to apply this? So the efficiency is eta, Greek letter eta, is 1 minus, oh, my cold sink was at 310 Kelvin, and my hot sink was at 2050 Kelvin. Right. You guys see do that in your calculator? Right. So let's see what's 1 minus parentheses 310 on 2050 close parentheses. Right. So this looks like 0.848. So, okay, I'll call that 0.85. Maybe I'll round it to. Okay. Hey guys, as a percentage, that's called what percent? 85%. Right. Would that be 85% efficiency? Again, this is ideal efficiency, but that's what was being asked. Right? So, say I had like this engine, and the cold sink was like 310 Kelvin, which is, and the hot sink was like 2050 Kelvin. Then you could get up to 85% efficiency. Okay. All right. You guys can do that. Standing waves. Okay, so now we're moving on to waves. Waves in harmonic motion. It can be set up. Remind you guys a few places you saw standing waves. Guys, if you pluck a guitar string, does the guitar string go up and down like that? I also took did I take a slinky one day and attach it to that doorknob and stretch it across the room and shake it up and down like that too? Give me a standing wave. It's got these nodes. You guys see these nodes right here? Okay. And then I did something different with the slinky. I shook up and down in such a way where it made like an S shape that kind of went up and down, right? Did something kind of like that. Okay. But it still had nodes because we're talking about standing waves. Right? These are like nodes. Boink, boink, boink. You guys see those nodes right there? Okay. And then there were like these antinodes that would move up and down. Okay. But you could reach up and you could touch it at the node and it wouldn't actually affect the wave, right? Still be a standing wave. Okay. Now, guys, is that transverse or longitudinal? It's transverse. Is this transverse? Okay. Can you set up standing waves that are longitudinal? You guys did. Do you guys remember taking the PVC pipe? You dunked it in the water. So dunking in water so you could make it longer or shorter. You could close off one end. Okay. Here, draw like a water vat down here. How about that? Got some water. And then you took a tuning fork and you struck the tuning fork above it. Right? Different tuning forks. Right? And then in some places it would resonate. Remember that? So it'd be like remember that as you would raise and lower the pipe. Right? Now remember the bottom is closed because the water level's here. So there'd be like a high pressure here. If you look at the air molecules, they'd all be like bunched up there. Okay? And then if you made this approximately 3 times the length, then about 2/3 of the way up, you get another like high pressure point. Okay? That's like a longitudinal version of this. That's also a standing wave, isn't it? Standing wave. Right? And sometimes it's easier to just like whip up a transverse representation, but you guys know it's actually longitudinal. So something like that, for example. Isn't it? Right, so you can set up transverse standing waves. You can set up longitudinal standing waves. Okay. Let's check out the answer choices. Standing waves can be set up by blowing across the top of a soda bottle. Yep, that sounds a lot like this lab you guys did. By strings of musical instruments. Yep, there's plucking a guitar string. By organ pipes. Okay, sounds back to like blowing across the top of a soda bottle, probably very similar principle, right? Or your lab. Okay. I like all those choices. Those could all be examples of standing waves. Those could all be standing waves. Right, you guys good? Suppose a bug is jiggling up and down and swimming towards you at the same time, compared to the frequency that the bug is emitting waves, the frequency that the waves is reaching you. Right, so let's get a bug in the water. Let's say the water's at rest and the bug starts out at rest and it's just jiggling up and down. Now it's sending out concentric circles of waves. Like if I mapped out the wave crest, it would look like just concentric circles. Okay. Now let's have the bug swimming to the right. So it's like starting to catch up to the very waves that it's sending out. Right, so it's sent out this wave at some point, send out this wave at some point, send out this wave at some point. Right, but it's like catching up to the very waves that it's sending out. You guys see that? Right. Okay. Now I just drew the wave crest. So if you're like down level with the water, it would look like blip, blip, blip. I'll try to think of that. Right? Versus behind the bug, it'd be like blip, blip, blip. Right, maybe something like that. Right? Right. Now, the premise of this question is the bug is swimming towards you. So here's you as the observer. The bug is swimming towards you. Right? Right. Let me ask a question that was not asked. Does the speed of the wave change? The fact that the bug is in motion. Does the speed of the wave change? No. Right. The speed of the wave doesn't change because once it's being released into the water, it just travels at whatever speed it goes. Right? Well, now the question that is being asked is about frequency. Guys, is the frequency reaching you higher or lower compared to not moving? It's higher frequency. And that's called the what effect? The Doppler effect. Boom. That's the Doppler effect. Right? So if it's swimming towards you, that's a higher frequency, isn't it? Right? You guys got that? As the sound of a car's horn passes and recedes away from you, the pitch of the horn seems to. Okay, let's go back to here. Let's just replace the bug with the car, and let's put you on the other side. Now you're this observer. Right? Didn't the car just go? Is that what just happened? Guys, is that a pitch increase or a pitch decrease? That's well, okay, yeah, okay. So it started high.
It's increase as it's leaving, it's a decrease.
Right, yeah. So it'd be a pitch decrease, right? Because it passed and receded away from you. That's a pitch decrease, right? It started high, it went low, right? Okay, so it decreased.
But it's both passing
Okay.
and receding at the same.
Okay, it started high, it became low, therefore it decreased. There you go, decrease. A child swings back and forth on a playground swing. If the child stands rather than sits, the time for a to and fro swing. Ooh, let's take a look at this. Okay. So I draw a couple of swings side by side. Okay. Actually, here, new paper. Let's get a new paper here. All right. Okay. So got swing, swing. Okay. Right, so we got these two side-by-side swings. Right. Now, saying something about the time to swing back and forth. Do you guys remember when you did a pendulum lab? The time period was like 2 pi times the square root of L over G. Right. Probably good to put in your notes. I mean, you have to exactly memorize that. Well, here, I'll point out exactly what you have to know to navigate to answer this question. Same questions on the exam as we're covering here. Okay. Right. So, here, I'll tell you kind of where this is going so you can see as the story plays out. Okay. Guys, the longer the pendulum you make, what happens to the time period to swing back and forth? More time. See, if you have a really short pendulum, it's like swing, 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 swing. If you have a long pendulum, it's like swing, 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 swing. Right. The longer the pendulum, the more the time to swing back and forth. Right. Now let's put these kids on the swings and see how this all connects. So one kid is sitting down. Right. Here's this kid sitting down. Right. You see that? Right. Maybe the center mass is like right here. And so the length of that pendulum is like this L1. Right. Isn't that true? Versus let's have a second kid and he's like standing. Right. and its center mass is like right here. I'll call that L2. Right? Ooh, do you guys see this is shorter than this? So by standing, you see he effectively makes this length shorter. Guys, if he makes the length shorter, this number's smaller. Well, how much time does it take to swing back and forth? More or less? Less time, right? The kid on the left maybe it's like swing, swing. The kid on the right is like swing, swing, right? Less time for this kid that's standing. The child swings back and forth on a playground swing. If he stands rather than sits, the time for a to and fro swing is shortened. Shortened time. Right, you guys got that? Suppose a simple pendulum is suspended in an elevator. When the elevator is accelerating upward, the time period of the pendulum. Okay, so we're still at time period of the pendulum. Let's take this to an elevator. All right, I have a pendulum in here. All right, this thing swinging back and forth. All right, I should tell you guys the time period is like from the left back to the left again. So it's a complete cycle, right? Okay. Now the time period is same thing as before, 2 pi square root L over G. Okay, that's all good. Okay. Now, what if you're just standing out on the sidewalk, or maybe the elevator is not moving, right? Or constant velocity for that matter. Okay. It takes some amount of time to swing back and forth. Right? This all plays out. Got some length here, got some gravity field. It's some time to swing back and forth. Okay, we got that. Okay. Let's play around with the gravity. And the first thing I want to do is actually go the opposite direction. What if you took this into space? Guys, if you took this into deep space, did you just turn off gravity? Just turned off gravity. Does this thing swing back and forth at all? No. Right, so you could say maybe it takes like infinite time to swing back and forth because it's never going to swing back and forth. Right, so it takes like forever. Okay, so then if you go the other way, what if you pump up gravity and you have like a ton of gravity? It's like, oh, I can barely stand. Right, this thing gonna swing back and forth really fast or really slow? Really fast. It's gonna go like, right? Okay. Now, how that plays out in the equation is it's like if you did G plus A, it's like what it's gonna be. And if you have an upward accelerating elevator, isn't that kind of what it feels like? Guys, upward accelerating elevator, are you gonna feel really heavy or really light? Really heavy. I'm gonna feel really heavy inside this elevator, right? That's like this. That's like you pumped up the gravity, which means it takes less time to swing back and forth, right? Guys see that? Okay. When the elevator is accelerating upward, the time period of the pendulum decreases. Less time to swing back and forth. Right, guys good? Right, are we good? A sound wave that has a higher frequency has a wavelength that is, okay. So I remember speed is equal to wavelength times frequency. Right? We got speed. This is the classic wave question. Wavelength frequency. Right. Let's draw a couple of waves here. I know it says sound wave, which is longitudinal, but I'm going to represent it as a transverse wave because it's easier to draw. Let's say one wave looks like this. And another wave looks like this. Okay. Right. And let's say they're the same type of wave, therefore they have the same speed. So whatever that speed is, it's the same speed. Okay. Guys, this first wave I drew has what kind of wavelength? Long or short? Long. In fact, the way you can calculate that or measure that is to go crest to crest is one way to get it. There's the wavelength right there. Right. So this is a long wavelength compared to like this crest to crest distance here. I'll call this like lambda1 and lambda2. How about that? Right. Is a short wavelength. Okay. Right. You guys got long and short wavelength. Right. Now, how about frequency? This first one, is this a high or a low frequency? Low frequency. Low frequency. Right. And this other one must be a high frequency. Right. Was that also true for electromagnetic waves? Like radio waves have a long wavelength and a low frequency. X-rays have a short wavelength and a high frequency. Okay. Now, sound is a different type of wave, but the same math sort of applies here. Okay. All right, you guys see that? All right. So higher frequency is a shorter wavelength. A leaf on a pond oscillates up and down 2 cycles each second as a water wave passes. 2 cycles per second. Okay. Let's say we got waves going through the water, and we're looking down at the side, and the water's going like bloop, bloop, bloop. Right? You guys see these waves like passing left to right, for example. Right? I'm gonna throw a leaf on here. Right, we're watching this leaf kind of bob up and down. Right? It's going like 2 cycles per second. That's like bloop, 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 bloop. I don't know if that's exact. That's close to 2 beats per second, isn't it? Right. Right. What is the frequency of that motion?
Is it half a hertz? 2 hertz.
2 hertz. 2 hertz. Guys, the frequency would be 2 cycles per second, which is 2 hertz. Right. Oh, no, you may have possibly been thinking of here. Right. Guys, isn't a frequency 1 over the time period? Or if you like, you could turn that around and say the time period is 1 over the frequency. Right? Now, frequency is in hertz, and time period is in seconds. Right. So here, let's ask a different question. Guys, if it's 2 cycles per second, that's like 2 hertz. 2 hertz frequency. How much time is there between bobs? The answer to that one is what? Half a second. Okay. So now if the frequency is 2 hertz, the time period is half a second. Okay. Right. Guess it. Right. Are we good? 2. 53. Radio waves travel at the speed of light, 300,000 kilometers per second. The wavelength of a radio wave at 200 megahertz is, right? Oh, so this sounds like an FM station kind of, or something pretty close to that. Okay. Let's do some math here. Okay. We'll do a few small math steps. Here, I got speed is equal to wavelength times frequency. Okay. We just did that a minute ago. But this is a special speed. It's the speed of light. Okay. Now, they told you the speed of light, but they gave it in kilometers per second. Let's convert that to base SI units. Guys, kilo is a factor of a what? 1,000. So I'm going to take 300,000 multiplied by 1,000 gives me 300 million meters per second. Okay. Oh, what was the question again? What's the wavelength? Actually, here, let me rearrange this in terms of variables. Because if you're solving for wavelength, can you just divide down frequency? So that'd be wavelength is equal to speed divided by frequency. Take this, rearrange it, make it look like that. Right. Okay. Right. Have this one of your notes. No algebra, you can do this. Okay. So wavelength is, we're looking at 300,000. Now that's kilometers per second. So I need to multiply by another 1,000 to get to meters per second. Oh, hey, look, that's 3 times 10 to the 8 meters per second. Of course it is. This is the speed of light, speed of radio waves, speed of all electromagnetic waves. 200 megahertz is the frequency. Okay, so something to do with 200. Now, they said megahertz. Guys, mega. What is mega? Mega is a what? Million. Mega is a million. How many zeros is that? 6. So you tag on 6 zeros. You guys know mega is a million, which is 6 zeros? Here, I'll write that up. Mega equals 10 to the 6, which is a million. Right? You guys remember that? Mega is 10 to the 6 or a million. Right? Are we good? Right. Okay. Cancel, 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 cancel. Hey, what is 3 divided by 2? 1.5, and then the units are going to play out to be meters. Okay. 1.5 meters. Right. That look good? You guys did do little conversions. Speed is wavelength times frequency, rearrange it, solve that. You guys get that? Right. Sound waves cannot travel where? Vacuum. Yeah. No. Electromagnetic waves can travel through vacuum, but sound needs a medium. Noise canceling earphones are an example of, right here. You guys remember if I have a taut string and I said a wave pulse this way, and I said another wave pulse this way? What do these two do when they cross over each other? Do they cancel out? At the moment they're crossing over, yes. And they'll actually, furthermore, they'll just like can't continue on. Now, this is a transverse example, but noise canceling headphones are the same thing, but longitudinal. They'll take the ambient sound, they'll invert it, cross it over on itself, and then it'll wash out all the sound and you hear nothing. Right? So that's called, what's that term called? destructive interference, destructive interference. Right, you guys remember destructive interference? Okay, right, you guys good there? Are we good? All right, well, bell's about to ring, so that's gonna be our pause point today.